Hello, this is Phil Barletta, Director of Operations of the NC State Nanofabrication Facility, and I'd like to talk about our Power America project dealing with process blocks of silicon carbide fabrication. Silicon carbide has been found to be a very important material for power devices. Although historically most power devices have been fabricated from silicon, the materials properties of silicon carbide are potentially more favorable for power applications. Specifically, the breakdown field of silicon carbide is nearly an order of magnitude higher than that of silicon, and its thermal conductivity is 3 times that of silicon. So these properties do enable silicon carbide-based devices to handle both larger voltages and larger currents than corresponding silicon-based devices. However, we have found that the economics of silicon carbide research can be a bit tricky. The reason being is because silicon carbide is a much higher temperature material, it requires very specialized, very expensive capital equipment, things like high temperature furnaces and ion implanters, and a lot of universities just don't have the dollars for that type of equipment. A lot of the industrial fabs, such as X-Fab and Wolfspeed, do. However, due to economies of scale, these big industrial fabs don't have the flexibility to work with single wafer and small lots and make it profitable. However, the university fabs, which do have that flexibility, don't have the dollars for the equipment. So how do we bridge that gap? How do we bridge the gap between universities that don't have the funding but have the flexibility with the industrial fabs who have the equipment but lack the flexibility? In order to deal with this issue, NC State University and X-Fab Texas are working to establish a development fab in the NC State Nanofabrication Facility. Power America is supporting the first steps in this process by funding development of a set of standard silicon carbide process blocks in NNF. This would allow for an efficient transfer of X-Fab production capability to a more flexible university facility and provide for a development opportunity for next generation process materials for silicon carbide devices. This model aligns with Power America's larger strategy, providing companies access to silicon carbide technology to accelerate innovation and adoption of silicon carbide power devices in mainstream applications. The NC State Nanofabrication Facility is well suited to take on this task. It's a Class 100, Class 1000 cleanroom located at NC State University Centennial campus. We provide semiconductor processing capabilities to various academic, industrial, and government clients. In fact, we have over 130 individual users in the NNF each year. And the NNF is a perfect example of the type of small, dynamic university fab that can quickly demonstrate unique breakthroughs in semiconductor fabrication. The specific process blocks that we developed at NNF were the definition of a hard mask for ion implant, the fabrication of a gate along with the electrode to that gate, an interlayer dielectric which electrically insulates the top metal layer from underlying gate structures, and ohmic contacts to the silicon carbide. So some of the details of the hard mask definition process block are given here, where we need to deposit the oxide, etch the mask, and then clean it for the next ion implant step. So the first thing we had to do is do some simulations to determine what thickness of oxide we would need. And the simulations showed us that 1.1 micron of thick SiO2 was sufficient for blocking the aluminum ions, arriving at a typical implant energy of 360 keV that is used in silicon carbide processing. So these SiO2 layers have been deposited via plasma-enhanced chemical vapor deposition, and we've actually increased the mask thickness to 1.4 micron to allow flexibility for higher energy implants. Once the oxide has been successfully deposited, the next step is to use photolithography to pattern the wafer with the structure that you want, and then etch the oxide, preferably with 90-degree sidewalls, all the way down until the silicon carbide is exposed. What this will do is allow ion implants into certain sections of the wafer, whereas other sections, the ones that have oxides on top, will be blocked. By using our I-line stepper and plasma etch tools in NNF, we're able to get the desired pattern with very sharp sidewalls and very well-defined features, which will be ideal for ion implantation. The next process block we studied at NNF was the gate fabrication process block, which involves the oxidation of the silicon carbide surface to form the gate, along with an electrode to the gate, which is deposition of a doped polysilicon layer and subsequent patterning. Now the oxidation process block is one of the more important process steps in a silicon carbide power device, as the quality of the oxide and the interface between the silicon carbide and the oxide is key for the performance of the device itself. The first thing we had to do with NNF was upgrade a pre-existing silicon oxidation furnace, because this pre-existing furnace only went up to 1100 degrees C. And as mentioned before, silicon carbide is a much higher temperature material, so we needed something that would go up to 1250 degrees C. So with Power America's support, we were able to make that equipment upgrade. And once we did that, the first thing we had to do was validate the performance of this upgraded furnace. So we did that with a silicon wafer. We loaded up a silicon wafer, oxidized it, and fabricated a silicon MOS, a silicon metal oxide semiconductor device with aluminum contacts, and we wanted to verify oxide quality. We were looking to make sure that we were able to get the oxide thickness that we wanted, as well as the breakdown voltage, and we were able to successfully do that with both of them. We wanted an oxide thickness of 50 nanometers. We were able to hit it at 49.7 nanometers, which is great. And we're also able to get the oxide breakdown voltage field at around 10.5 megavolts per centimeter, which is exactly what you would predict as oxide breakdown. So we're able to demonstrate that, at least for silicon, we're able to get the oxide quality that we needed from the new furnace. The next step, of course, was to oxidize silicon carbide and make a similar, instead of a silicon metal oxide semiconductor device, make a silicon carbide metal oxide semiconductor device. And we were able to go ahead and do that at high temperature, make the oxidize silicon carbide and make the device. And we were particularly pleased with these results. First of all, as you can see from the graphs here, the results of the CV graphs are very consistent, die to die. There's minimal hysteresis. There's a very sharp slope, which indicates high quality oxide. And again, we were able to hit the thickness right in the range where we wanted it. We got anywhere from 42.3 to 42.6 nanometers in thickness, which is very well in line with the 50 nanometers that we were expecting. We also took the silicon carbide MOS device and measured some IV data and wanted to look at the oxide breakdown. And once again, we got very, very consistent results, which is key for this type of project. And the breakdown voltage at 11.3 megavolts per centimeter is an excellent number. It indicates we have an oxide of excellent quality on our silicon carbide. The next process block we took a look at was the interlayer dielectric, or ILD, process block. And what the ILD is the silicon dioxide layer, which insulates the top metal contacts from the underlying gate structure of your device. And the primary challenge of this block is the need for an oxide layer with smooth, rounded features, as opposed to the sharp, angular features you typically get from etch and lithography. So we had to develop a whole new lithography technique in order to get the rounded features like you see here in the SEM image. And we're currently undergoing etch trials in order to see if we can transfer the rounded lithography features into the etch as well. And one of the interesting things we've done with this is we've been able to incorporate design of experiments using SAS's JMP software to maximize the results in this process block. So it's given us some very positive results and allowed us to maximize the results in less time. The fourth and final process block to look at was the ohmic contact block. And basically what we're doing is forming the ohmic contacts of nickel silicide to silicon carbide. That involves the e-beam evaporation of about 1,000 angstroms of nickel and a post-deposition anneal to form the silicide. And then we can etch away using a wet etch, which will not anneal away any of the silicide, so it's essentially a self-aligned etch process. From that point, we'll measure the specific contact resistivity via transmission line method and get the contact resistivity of the ohmic contacts. The most challenging part of this process is actually going to be the ion implantation, which is something we can't do on campus. We need to go ahead and have this outsourced. So we've identified the vendor for this. We've sent the vendors the wafers and the implant schedule, and we're in the process of getting that work done. Afterwards, we will go ahead and do an anneal, a high temperature anneal, to activate the dopants and then wrap up the ohmic contact block, which will also mean that we'll wrap up the project which NNF has enjoyed working out thoroughly.